do my psych exam. I'm going to do my math homework.
I did get emailed some questions from 3.2 on Wiley Plus, so we'll go ahead and take a look at that together. Number 9. Now some of you might have to enable Flash. If you have to enable Flash, then the padlock up here is where you would get that setting. So you click on the padlock. I can click on Flash right here, but on some browsers I've noticed I have to go to Site Settings to get to Flash. So let's review where we were at with this question. If we let n stand for the set of all natural numbers, then we write 7n for the set of natural numbers all multiplied by 7. So we have the multiples of 7. Show that the sets n and 7n have the same cardinality by describing an explicit one-to-one correspondence between the two sets. So let's review one-to-one correspondences using this problem. So we have the set n, the natural numbers, 1, 2, 3, 4, 5, dot, dot, dot. This is a good quiz question, by the way, and you'll need the dot, dot, dots on your quiz to show me you realize this set goes on forever. And then 7n, so multiples of 7, 7, 14, 21, 28, 35, dot, 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 because that set goes on forever also. And we said that two sets are the same size if and only if there's a one-to-one correspondence between each of the two sets. So each element of the first set gets assigned an element of the second set. So here I can show that one-to-one correspondence by having 1 go with 7, 2 with 14, 3 with 21, 4 with 28, 5 with 35. Thank you. And then we check. Is each element used? Did I miss any of those numbers in those sets? Didn't miss any. Is any used twice? No. So we have a one-to-one correspondence. Each element in the first set is assigned to exactly one element in the second set. And so these elements, these two sets have the same cardinality. They're the same size. Which again is kind of startling because it seems like 7n should be 1/7 of the natural numbers in size. But in fact, they are in a one-to-one correspondence, and so they have exactly the same size. Well, you can't very well draw these double arrows in Wiley. So what you're supposed to do in Wiley is to put 7 and then the times on top of the number 8, 7 times n. So there's an n in the natural numbers, and 7 times n goes with that. So 1 goes with 7, 2 goes with 14, and so on. So that's how we describe that in this case. I believe it's case sensitive. I think if I put a capital N, it's not going to work. Let's try that once. Yeah, so you can't use a 7 times a capital N. And that's because they have a little lowercase n right here, and so you're supposed to show that this little lowercase n is what you're multiplying by 7. Does anybody have other questions to go over? Well, you'll have a different multiple than 7 probably, right? You'll probably have multiples of 3 or 4 or 5 or something like that. We were working in section 3.2. We were in search of a set that had a cardinality larger than n. So far, n is all we've found. We've found several sets that look like they should be larger than n or smaller than n, and yet they were the same size as n. Our latest quest was to see how much bigger is the set of rational numbers than the set of natural numbers. So the rational numbers are all the ratios, all of the fractions. And we started on that because we wanted to list, just like we listed the 7n, we wanted to list the rational numbers. So we made a nice list up here. We took all the fractions who had a 1 in the numerator and made a column out of those, and then all the fractions with a 2 in the numerator, a 3 in the numerator, a 4 in the numerator, and so on. So we can find any fraction in our list. Our list has all the fractions. I'm going to go the other way here. So for example, if you wanted to find 99 over 100, you go out 99 columns and up 100 rows, and there would be the 99 over 100 off of our list. But that's what the dot, dot, dots mean, that we're going to have these lists continue forever and in the negative direction as well. So I had asked you to think about this list and see if you see any problems with it as we work to put it into a one-to-one correspondence with the natural numbers. Does anybody see any problems with it? Did you give it any thought over the last couple days? Let's think about what we're doing. We're going to take the natural numbers. So let's start that off. 1, 2, 3, 4, 5, 6, dot, 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 to show that goes on forever. And we want to find a one-to-one correspondence with the rational numbers. So we want to do what we did in this homework problem. A one-to-one correspondence. So none are missed. Each element gets used, and none are used twice. Okay. Now with that in mind, do you see any problems with what we have started here? Well, let's start getting the list ordered so that we can make a one-to-one correspondence. And your author does this in our textbook. He starts here with 0. And then he spirals out from there. So he goes from 0 to 1 and then to -1, and we're going to continue the spiral. So what we're saying is that the number 1 in the natural numbers goes with 0 in the rational numbers. The number 2 in the natural numbers goes with 1 in the rational numbers. The number -1 goes with the natural number 3, and so on, and we'll continue that spiral. So that brings us to 2. So 4 goes with 2. Now, is anybody seeing any problems here? Well, the problem is that we have only got a one-to-one correspondence if every element is used, which is going to be okay because we can see a way to spiral through all of these now. Also, none can be used twice. And some of these are repeats, right? Some of these fractions have the same name, but they're the same values as fractions with different names. I don't think I said that right. Some of these fractions are the same value, like 2 over 2. That's the same as 1. Well, we can't use fractions twice. None of these elements can be used twice. So 2 over 2 is 1, so I'm going to cross it out. So that's the provision that we're going to make. Whenever we come to a fraction that's a repeat, we'll cross it out. So we'll keep going through our spirals so we don't miss any. And if we come to a fraction that's a repeat, same number, different name, we'll cross it off. So -2's, that's -1, and we'll cross it off. And we come to -1/2, and we keep going. We have 3 over 1, 3 over 2, 3 over 3 we're going to need to cross off because that's the same as 1. 2 over 3, 1 over 3. We'll keep going here. So we'll cross off -3 over 3. That's the same as -1. And we just keep going through the spiral, but as we come to any repeats, we cross them off. For example, 4 over 2, that's 2. So I'm going to cross off 4 over 2. So the spiral continues on forever, and we're not going to miss any numbers. And because we're crossing off any values that are equivalent, we won't use any twice either. So we'll just write a couple more in our list here. Let's see, I was at 2. I crossed off 2 over 2. That brought me to a half. So 5 goes with a half. After a half came -2, so 6 goes with -2. And I'll go dot, dot, dot. So we do have a listing now. We have a listing of the rational numbers where none are used twice and everyone is listed. We haven't missed any. None are used twice, or 3 or 4 times even. None are used twice at all. And none are missed. So we have a 1-to-1 correspondence. None are used twice, none are missed. There's a 1-to-1 correspondence between the natural numbers and the rational numbers. And that's just really remarkable because remember, between every 2 rational numbers is another rational number. In fact, there's an infinite number of rational numbers between every 2 rational numbers. So between every 2 of these numbers, every 2 of these fractions up here, there's an infinite number of fractions. That's not the case with the natural numbers. There's not another natural number between 3 and 4. Or between 4 and 5. Yet because we are able to arrange them in such a way that we don't miss any of those fractions, we are able to create a 1-to-1 correspondence. So the rational numbers, I'll just abbreviate that with a Q with a double bar. The rational numbers are the same size set as the natural numbers. Okay, they have the same cardinality. They have the same cardinality. So the question that the author asked us at the beginning of this section was how much bigger is the set of rational numbers, Q double bar, how much bigger is the rational numbers, abbreviated capital Q with a double bar, than the natural numbers? Well, what is the answer to that? First question for the day, how much bigger is the set of rational numbers than the set of natural numbers? What's the answer? This is your class activity, so you'll want to figure this out. What is the answer? What did someone say? They're the same size, right? The rational numbers are not bigger than the natural numbers. They are the same size. So you can just underline that, and you can go ahead and submit that as your class activity. So you can take a picture with your name on there somehow. Or if it's easier, you can type it in. I don't know if that's easier, though. I feel like you have to submit something anyway. So we're not doing so well finding a larger infinity than the natural numbers. That's okay. We'll be moving on into 3.3 and look further there. But for now, we're going to take a look at an experiment. So we're going to have an experiment. The experiment lasts 1 minute. Experiment only lasts 1 minute, so we have this clicking this ticking clock. So we're going to perform an infinite number of tasks in 1 minute. We'll label the tasks 1, 2, 3, 4, 5, ... because we're going to do an infinite number of tasks in 1 minute. So we're going to split the clock minute into infinite little sections. Here's how we split it up. Okay, so the first task we're going to do in half the time that we have, 1/2 minute. Then the second task will take half of the remaining time. So half a minute is gone, but now we have 1/2 minute left, and a half of that, or a fourth of a minute, will be used to do the second task. And then we've used up a half and a fourth. That leaves 1/4 left. Well, we're going to cut that in half as well and have 1/8 of a minute. And then we take the 1/8 of a minute that's left, because now there's only 1/8 of a minute left, because remember, we keep cutting the remaining time in half. We'll have a 1/16 of a minute. And for the fifth task, we're going to have to go faster and faster, because now we only have a 32nd of a minute left. In fact, the nth task, you can tell how much time you have, because these are all multiples of 1/2, right? 1/2 times a half is a fourth. A fourth times a half is an eighth. An eighth times a half is a 16th. So by the time we get to the nth task, we're down to 1/2 to the n power minute. Now this might get so tiny on your calculator that you don't have enough decimal places to show this tiny amount. But that doesn't mean that it's 0 time. It means that it's so tiny your calculator ran out of decimals to show it. Because remember, our decimal expansions can go on forever. So we can always take the remaining amount of time we have and divide it in 2 and get a tinier little amount. So these tasks, we have infinite tasks to complete. And here's what the tasks are. We're going to take a barrel. Okay, so we're going to take a barrel. It's a gigantic barrel. And we're going to take a trough, and from the trough we're going to dump ping pong balls into the barrel. Now these ping pong balls are numbered. They're numbered 1, 2, 3, 4, 5, 6, 7, and so on. So we have this big barrel, and we're dumping ping pong balls that are labeled 1, 2, 3, 4, 5, etc. into the barrel. And we're going to do this in this way. So we're going to take, during our first time increment, our first half a minute, our first task we will add balls labeled 1 through 10. And then, that's not the only part of what you have to do on that task. You also have to remove a ball. So we're going to dump in balls labeled 1 through 10, and we're going to remove the ball labeled 1. Okay, so remember, each of these balls has a little label on it. We're going to take out the ball that has the number 1 on. So you're going to dig around in your half minute, grab the one labeled 1, and chuck it out. Now, second task, during the next 1/4 minute, we're going to dump in the balls labeled 11 through 20, and reach in and throw out the ball labeled number 2. Third task, in the next 1/8 of a minute, you're going to dump in balls 21 through 30, and they just keep coming. You don't have to worry about that. But you get to reach in, grab ball labeled number 3, throw it out. You have to dig around a little harder there, okay? And we just keep going faster and faster, because now you're down to a 1/16 of a minute. Balls 31 through 40 come pouring in the barrel. You reach in, grab ball number 4, and throw it out. And we just keep going in this way, and you're going faster and faster. For this minute, you have superpowers of fastness. If you ever wanted to be Flash, that's you, okay? All right. So this experiment lasts a minute, and then bing, timer stops, minute's over. And the question I have for you is, How many balls are in the barrel? How many balls are in the barrel after the 1 minute ends? How many balls are in the barrel after the 1 minute is over? Okay, so 10 balls come in, you reach in, grab one, throw it out. This goes on for an infinite number of tasks. But the minute ends, boom. What's left in the barrel? Okay, so I'd like you to talk about this in your groups. Online students, I encourage you to find someone to talk about this with. It's a lot of fun. This is how my husband and I spend date night. We have the best marriage ever. 33 years, so it must be doing something right. Okay. All right, so talk about this in your groups. I'll help you get in the group if you're not in a group. Okay.
Like your minute keeps getting down there.
Because it's half of that, 15, so that's 45.
And then you keep adding balls. You take out.
Yeah, so no matter where you end up in the minute, you're going to add up all the balls that went in there. You're going to have your total amount of balls that went in there in the whole minute, and then you're going to subtract how many you took out. So yes, they to find the exact number, that's how you would do it.
So you would take, more balls, and then you would subtract how many balls to get how many is in there. That's how you would, so like you did an equation. Unless you stop, you only have 5 laps, then you just figure it out.
Depends if we're talking about
Yeah. Then it'll keep going. But if it's an actual infinite.
You said finite.
Infinite.
No, you said finite.
I'm an infinite. Oh my god, just because I said so, but if, let's say, you only have 5 tasks, then you would take 50 minus 5.
Because eventually a minute ends.
I suppose like I'm
But in this scenario, a minute keeps just getting fractions of time. That's extended.
And then like you have to like the previous one until you add a
And so actually that will take me
that's why I'm like,
Where'd you get the white on it? We don't keep
that was my problem.
So how long are you driving?
So it's not because we keep cutting it in half. And he keeps going at minutes, so like 20 minutes. Right. So once we're at 20 balls for the solo that came in. So yeah.
And they have to be
There's 50 balls and then none of your men, maybe it's like or they did with it. So if you put 1 over 2 is different. It's either oh yeah. Well, yeah. If you keep the same like 1 minute.
Oh no, I know, I was not.
I was thinking 2 So I mean, at some point it would become humanly impossible, but obviously we're not talking about that. So, I was thinking 2 undecided. What is We had just kind of said that it's gonna go on forever, and it's just kind of infinite, because, you don't know how many you're gonna have after a minute, and then you're gonna kind of subtract, like, however many total you pulled out, or whatever, from the total balls that went in there. That's what we're gonna do.
So you're leaning toward infinite because you're throwing in 10. and
Yeah.
Okay.
Because you could go on forever for a minute.
Okay. Well, let's talk about it together for a few minutes, okay? See if we can move forward a bit. So I'm hearing a lot of infinite balls in the barrel because every task you throw in 10 balls. 10 balls come pouring in and you only take out 1, so that leaves 9 for every task that are extra in the barrel. So I hear a lot of people saying infinite number of balls. So what I'm going to ask you is, if there's an infinite number of balls, what is the number on one of those balls? What is the number on one of the balls in the barrel? Okay, so could it be the ball labeled 100? Could it be the ball labeled 1,000? Could it be the ball labeled 10,000? So I'd like you to think about this again with that in mind, okay? What is the number on one of the balls in the barrel? Okay. Clock is ticking again.
Well, then we'll take a while to get up to because you're slowly pulling up. Yeah, you're slowly pulling up. Ready and tell me. Satisfactory.
What is the number of one of the balls that's in there?
Hey, I made a heart.
So is this one the one that is equal?
That's how many
Means it would be any of these?
You did a good job. I'd love to hear all of your discussion. Okay, so I think I've heard that this 100th ball is not in there because you had eventually a 100th task, and that 100th ball got thrown out with the 100th task. Same thing with the 1,000th ball and the 10,000th ball, because eventually you came to the 1,000th task, and at that point you threw out the 1,000th ball really quick, because by that time you're moving really quick. And the same thing with the 10,000th ball. You'd have a 10,000th task eventually, and at that point you'd throw out the 10,000th ball. Now I'm going to give you another hint. This is that the balls are added 10 at a time is a red herring. What's a red herring?
Something to throw you off.
Something to throw you off. Yes, it's a literary device. So something to throw you off. That's a red herring. Suppose all the balls were in the barrel to start with. Suppose all the balls are in the barrel to start. Okay, then you can talk in your groups again, okay? And let me know how many balls are in the barrel after the minute ends.
For the time slot thing,
Because if you did the tasks and the balls are moved,
right, but that's not a minute.
and if there's like a certain
Possible.
Eventually you're gonna run out.
but if you remove them, yeah.
I'm saying that these two are gonna be different sizes. There's two sets of each different sizes.
Because the minute will keep going.
Okay, class. How many balls are in the barrel after 1 minute? I heard a couple of you had it. What's the answer? Done. Good, good. I heard a couple of you had it. Good. No balls are in the barrel after 1 minute because you have thrown out every single ball at the prescribed task. So the millionth ball isn't in there because you had a millionth task and you threw it out. And I heard some of you saying one-to-one correspondence. There's a one-to-one correspondence between the number of tasks you're doing and the number on the ball. So each time your task came, you threw that ball out. And since you had an infinite number of tasks that you completed in that 1 minute, you threw out every single ball. So that's that's kind of a mind twister, and I hope you'll spend some time thinking about that and talking about it with some friends. I never did convince my husband the barrel was empty. All right. Well, we're going to go on to section 3.3, where we continue in our search for larger infinities. In 3.3, we begin to look at Cantor's work. He was working around 1872. Here's a picture of George Cantor. He proved that the set of real numbers has more elements than the set of natural numbers. So we're going to spend some time figuring out how we figured that out. Now, this wasn't easy for the mathematical community to absorb. When Cantor conceived his idea near the end of the 19th century, many mathematicians resisted it strongly and attacked Cantor in a personal, abusive manner. These attacks, combined with other psychological issues, contributed to a bleak existence for Cantor, who spent much of the last part of his life in an insane asylum. Remember the Pythagorean disciples who threw one of their members into the ocean to drown because he revealed there were irrational numbers, not just rational? Some mathematicians feel very strongly about their ideas. All right. But for those mathematicians who were deeply immersed in such issues, the idea of having many different infinities was a tremendous blow. Out of vague and ill-defined notions of sizes of sets, Cantor distilled the fundamental idea of one-to-one correspondence. This idea is so basic that one feels compelled to accept its logical consequences, right? When we did one-to-one correspondence with finite sets, you're like, oh yeah, that totally makes sense that two sets are the same size, if and only if there's a one-to-one correspondence. But these consequences contradict the intuition of most people until their intuition is adjusted, after which the concept of more than one infinity becomes perfectly natural. Thanks to Cantor, who reached out and considered the counterintuitive, no mathematician today has a problem encompassing the idea of multiple infinities. Well, we're going to join those ranks as we look in 3.3 and look at the real numbers. So I kind of gave away the answer to the first question, 3.3. Is there an infinite set bigger than the natural numbers? And I read to you there that there is, in fact. So up till now, though, we've only found the natural numbers, the integers, and the fractions, the rational numbers, to all have the same size cardinality. All have the same cardinality as n. Okay, so the natural numbers Remember, those are the numbers 1, 2, 3, dot, dot, dot. The integers, those are the negative natural numbers, 0 and the natural numbers. So we list out those numbers going to infinity on the left and going to infinity on the right. And the rational numbers labeled Q for quotient, those are the fractions. So those are the numbers that we've looked at so far, or subsets of those, and they all have the same cardinality as n. So now we're looking at larger infinities. I don't know if you remember, but on the very first day of class we played a game called Dodgeball, and at that time I told you that was going to help us understand different sizes of infinities. So that's what we're going to do for today, spend some time looking at dodgeball. Online students, you can go ahead and print out this dodgeball scorecard. If you want to try this at home with a friend, this is on Canvas, on the class activity materials. So remember, player 1 makes a row of X's and O's, however they like. And then player 2 only gets to do one box, an X or an O. And then player 1 goes and makes a whole row of X's and O's again, and player 2 gets to do one row. Now while we're doing this, player 1 wants a match. So really, player 1 should start watching what player 2 is doing. So player 1 wins if there's a match. Player 2 wins if there is not a match. Player 2 is dodging. Okay, and the row would have to match, not like columns or diagonals or something. The row would have to match. So player 1 is going to copy player 2 as much as they can, and player 2 is going to avoid what player 1 is doing. That was dumb. I'm not going to win for there for sure. Okay. So player 1 wants a match. Player 2 only gets to pick one box, and they're going to do, they're going to win if there is no match. So let's see, I don't see a match. Do you see a match? No. No match. Okay, so player 2 wins because there's no match. So there was a winning strategy. Does there anyone remember who had the winning strategy, player 1 or player 2? Yeah, it's player 2. Okay, so play as much as you need to until you can get that winning strategy down, because then you'll be ready to look at different sizes of infinity. So I'll just send some down each row here. Play each other, okay? Play in pairs, and take turns being player 2. So you can make sure you get how to win. Make sure there's 2 of you. I think there's enough to be pairs.
Isn't it to win player 1?
Nicholas is going to come and join you.
Right?
Nicholas is going to come and join you, so you both get lots of turns at being player 2. Yep. Oh, wait, I do.
It's a double set.
Yeah, go first.
I'll be player 1.
Yeah, so you can go whole row. I don't think you were in rolling class at first. This is like totally just play. Okay.
I'll be 2.
You remember the winning strategy? I know. Okay. What? You remember the winning strategy? Yeah. Okay. You're supposed to try. Well, after you play a little bit, see if it comes to mind. Otherwise, I'll.
I think I only won once. I think.
Now, once one of you understands the winning strategy, make sure you get a chance to each play as the winning strategy, okay? No.
I don't even know how. I was like, wait.
Just the diagonal.
See, I started digging into your children right when you're here and realizing, did you remember that?
No, we have to
Okay, so you have to do.
You win.
Couldn't possibly.
Yeah. So as player 2, do that.
I think the two of us were saying we can do something. Do you remember?
I messed up on the first five.
Okay, okay, no matter what.
Yeah, you win because
That's
I copied it.
Okay, all right.
I would have put an O there, I would have won. Because you would never have had.
So then she got it. Okay, we'll try again. This time, both of you need to win it as player 2.
Okay.
So, do you remember the winning strategy for player 2?
You just do. Yeah.
Yeah. Yeah, okay. Who won it? Okay, you player 2 won? Do you remember the strategy to do that? I'm going to remind everybody what to do to win, okay? Okay, so once player 1 makes their roll, whatever they do, player 2 can be the opposite all the time if they pay attention to which box on the first row. First box, right? So if they're different on the first box on the first row, then they'll be different from that row. And then player 2 can try matching. Player 1 can try matching, but as long as player 2 keeps looking at that diagonal and does the opposite of what's on the diagonal, player 1 is not going to be able to catch up. Okay, so pay attention to the diagonal and do the opposite. You can keep playing and make sure everybody gets a chance to win as player 2.
I know. I wasn't paying attention.
Oh.
Yep. It's okay.
That's why we avoid out.
As long as you're playing for yourself.
There you go.
Okay, player 2. Just follow diagonal. Do the opposite.
Do the opposite of the diagonal, and then you'll always be different from that row.
Wow, you're
I know I did.
Alright.
I don't really care at this point. You're gonna win anyway.
Okay, so make sure everybody gets a chance to win as player 2. If you didn't win as player 2 and you have a question, make sure you raise your hand because you
Don't I want the same thing with you, or what?
Oh.
Right?
Oh. Pick one.
See ya. I kind of forgot what I was doing.
I might win this one.
So, did you decide what you're gonna do? Are you going to LL or are you skipping the next one?
Skip.
GG.
So we have a way for player 2 to win all the time. They just have to be paying attention, and they'll be different from row 1 in box 1. They'll be different from row 2 in box 2. They'll be different from row 3 in box 3, and so on. Now I'm going to make it harder.
What?
Now I'm going to make it harder. Can player one win? Can player one win if they can list as many rows as they like? Can player one win if they can list as many rows as they like before player two lists anything? So can player one win if they can list as many rows as they like before player two lists anything? So if player two is not going to go at all, and player one's going to extend their board and make as many rows as they want. Maybe they even switch over to notebook paper and fill out as many rows as they want to. Player two has to sit and watch. So each of you try this, okay? Each of you try being player one, and now you get to list as much as you want to before player two goes. So there are grids on the back. Whoops, mine's used on both sides, okay? So turn your sheets over and list as many rows as you want and see if you think you can come up with a way for player one to win, not player two, but for player one to win by listing as many rows as you want. Okay, so each of you starts out as a player one. If you need another sheet, raise your hand, I'll bring it by.
Okay.
Another sheet.
We're good.
Okay. Do you want me to go for player one first?
Yeah. Let's both just do it and then we have it.
So you're both player one. Yep, because you're both going to list as many rows as you want before player two gets to it. Here's another sheet. You both be player one. Yep. So be player one. As many rows as you want.
So I just start filling in whatever.
That's going to be a nice
You're both being player one now. You fill out as many rows as you want to. So did you fill out as many rows as you want to? Yes. You should do more. Do more. Do more rows. Be creative.
I'm running on things to do already.
You don't have to be limited by the size of the paper. You can add on your notebook paper. There should only be 6 columns though. So you don't need a 7th column, just more rows.
I'm gonna repeat myself.
I know, I probably am too.
So I see you are busy working. Did anybody decide an answer to this? What's the answer?
Could be here forever.
Not forever, but a long time. And then, could you win?
Yes.
Yes. How come you could win as player one if you can list as many rows as you want?
There's not an infinite amount of X's and O's you can put in 5 spaces.
Good. There's not an infinite amount. There's not an infinite amount of patterns. So you can, you don't even need your super speed skills to do this. You do need some time though, because there's actually 64 patterns. 64 patterns of X's and O's. That's why I didn't let you keep going. But was that the strategy you were trying, player one? Good. Were you trying to think of all the patterns possible? You can do that when you only have 6 squares. Okay. So that is the strategy for player one to win if you go ahead before player two. Okay, that's as far as we get today. So think about dodgeball over the next couple of days, please. And then on Friday, we'll come back together again and talk about real numbers being larger than the rational numbers.
Would you like the extras?
Thank you, that would be delightful.
Pretty.